Good morning, everybody. So I'm Damien Cauquil from a French IT security company. I'm going to present here a new tool to handle some specific chips from NXP. So first of all, I'm the head of R&D at Econocom Digital Security, which is a French IT security company, and we created the first IoT cert. So basically, we are working on a lot of devices, connected devices, and also industrial devices. And this is where this talk comes from. I'm also a senior security researcher and also a hardware hacker, or at least pretending to be one. But, I don't know everything. So what we're going to talk about? So we're going to talk about firmware extraction 101. I don't know if you are familiar with this firmware extraction process we are used to do when it comes to analyzing embedded devices. But in fact, I'm going to go through this process, and we're going to see that sometimes it may fail, and it requires a lot more work to find a solution for some issues we can meet. So we then are going to go through the IMX architecture, and especially its memory layout, what is very interesting here. And I will then present my tool, my new tool, IMX NAND tools. So it's more than a tool, just a set of tools that will ease the work on IMX non-flash dumps. And we will conclude with some best practices for IMX systems designer. So first of all, the firmware extraction process. When you are doing some kind of analysis of a specific device, you need to know what a device does. So this device can contain a lot of data, such as file systems, applications, binary files. So sometimes it's just some kind of a single program that runs on the system. So this is something we want to extract from a device, because by doing this, we can be able to understand how this device works and what data does this device manipulate. So this is very interesting. And also in this data, we expect to find some very interesting stuff, such as encryption keys, decryption keys, certificates, passwords, and sometimes also intellectual property, so some specific algorithm implemented in the device. So this is something very useful when you are analyzing this, say, your device. So you need to understand everything about a device. You need to determine how this device has been created, has been designed. You need to understand also how it works. And this is very specific here because, vendors pretend to know that they pretend to know how the devices work, but in fact, they do not, because there is a gap between the vision of how a device works from a designer perspective and the way the device really works. There are in between some developers that sometimes do mistakes, and these mistakes introduce some vulnerabilities in many devices. So they might think that a device works a specific way, but in fact, it can work differently. So this is why we are going to analyze this device, and this is why we are trying to determine how a device works. And also, we need to know what data is stored where is stored what data. We need to know where you can find the interesting data. So the first method you can use is to buy a small clip for your chip that contains all the memory, which is basically some non-flash chip. And by using this clip, you can just plug it on the chip and use some kind of adapter to extract the content of the memory. So this method may work, but sometimes it may not, because once you power the non-flash chip, then the whole system will going to start and interact with this chip. So this is sometimes a problem, because since you are going to interact with this chip, you won't get the correct data, since another device or component is actually interacting with it also. So this is one method to do it, but we prefer the second one, which is a chip-off. We are going to remove the flash memory component from a PCB by using some tools. So here I'm going to remove this flash chip with a hot air rework station. So this is the big stuff I'm using here. And so it takes, sometimes it's a few minutes to get it removed from the PCB. So you have to be careful when you are doing this, because you can burn the chip. You can fry the chip if you set the temperature of this hot air rework station too high. So it needs some kind of practice to be able to extract this one. So this one was a bit difficult to extract, and yeah, here it is. So here I removed this chip, and then it's ready to be dumped. So in order to extract data from this flash memory, you need some specific stuff. And this stuff is a professional flash programmer. So this is a specific device. There are many of them. I put 2 of them on the sides. On the left side of this slide, you got a Dataman, which is a very professional flash memory reader, and an eraser and programmer. And on the right side of the slide, you got the TNM 5000. So this is a Chinese version of the first one, and it works very well. But in fact, it only works with on Windows with some specific drivers you need to install, and it's quite a challenge to get it working on Windows. But once it works, that's okay. You can use it, and it comes with a lot of adapters. These tiny green boards you can see here with a lot of various sockets to put the memories in them. So I'm going to plug this tiny non-flash memory inside this socket. So remember, be very careful when you're doing this, because you need to be sure that pin 1 on the flash chip is connected to the pin 1 on this adapter. If you don't do this, you are going to fry the memory and everything is gone. So again, take some time to do it. So once you got your adapter socket ready with the flash chip in it, then you can plug it in a ZIF socket. So ZIF is zero insertion force. So this is a very nice socket. You can just you maneuver the lever, and then you can plug this adapter and use the programmer with it. And last but not least, we are going to use this programmer to extract the firmware. So it takes some time. Here, I think the video is has been modified to go faster than it actually does. It took me maybe 10 minutes to extract the content of this flash memory, 1 GB flash memory. So this is something very, we are used to it. We know how to do it. We do it very, 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 very commonly. So this is a well-known process, and it's also documented. If you have a look at the dump you got from this programmer, then you will see that this dump is not a 1 GB dump. Since your flash chip is supposed to contain 1 GB data, then you will see that it's a 1.1 GB data stored in it. So why do we have more memory than expected? The reason is that these non-flash chips are storing data a very specific way. So we are going to talk about pages, bytes, and what we are used to call OOB for out-of-band data. In a non-flash chip, bytes are stored in pages. If you want to modify a byte in a flash chip, you cannot modify just 1 byte. You need to read a page, modify the byte in this page, and then write again this page. So this page has a given size. This is described in the documentation, the datasheet of this chip. And this is quite useful. But also, these non-flash chips are very prone to errors. They are not 100% reliable. So what does a manufacturer do? They put some extra space in them to allow some more data to be stored. And basically, this extra space is used to store some ECC bytes. So ECC bytes, so ECC stands for error correction codes. These are specific data computed with some algorithm that allows a driver or a controller to detect errors in the readings and then fix these errors. If you have a look more specifically at the layout of this non-flash, so you will find two different main layout used by non-flash drivers or controllers. So the first one on the left puts an extra space after each page. So you get the page of data, then some bytes of OOB data, then another page, another OOB data, and so on. And there is another layout where all the OOB data is stored in one page, for instance, or maybe multiple pages, depending on the flash chip size. So if you have a look at the datasheet, you will find that all of this information in the datasheet, such as the page size, which is here 4,320 bytes, composed of two series of bytes, one of 4,096 bytes, which is basically the data size stored in one page, and the 224 bytes, which is the OOB data. So here we have a very nice clue about the layout used to store the data in the flash chip. So this is very common. So we create some script in Python to remove this out-of-band data. So what we are going to do is just load in memory the whole content of the file. Then we are going to remove for each page this OOB data and concatenate the results. And then we got a cool flash memory dump without the OOB data. Then we can process it with some tools. So here it is. And then we are going to check if this dump is okay. So let's use Beanwalk. Beanwalk is a very standard tool, very well-known tool to handle this flash. And then it finds a lot of file systems in it. 4 SquashFS file systems and 2 GFFS2 file systems. So that's cool. Yeah, that's good if my clicker works. So I think it's out of battery. So there are many file systems that can be used to store data on this flash, and we go very quickly through this file system. So you can find some SquashFS file systems, UFFS2, yet another FlashFS file systems, GFFS2 also, journalist flash file system version 2 with one partition per image, and also a more recent file system, more recent system of data storing, which is UBI for unsorted block image, and we go further with this. So basically, at this moment, we extracted the flash memory chip, we dumped all the contents of this, we ran Beanwalk, and we got everything we need. So next step is to try to extract information, files, configuration, and so on from the flash chip, from this dump, sorry. So this process is, as I said, is very well documented. And recently, Pentest Partners published a blog entry on this process. So everything is a bit more detailed than what I presented here. So if you want to have more information about this process and go further or try it by yourself, go to this blog post. This is very, very detailed and complete. So we know how to do this. Yeah, that's okay. This is well known. But at a specific time, a customer asked us to help him with some kind of system he had, and he was stuck. This system is an IMX6 platform. So what is this IMX6 platform? It's something created by Freescale, and this system is very particular. And well, we told our client, our customers that, yeah, we can do it. We know how to do it. Yeah, this is something we are used to do. Sorry. Yeah, give us this platform. We are going to extract the chip and get all the data you want from this, because this customer was not able to do so. So yeah, we go through it. We dump the flash, extracted the flash, do the exact same thing as I showed you. And at the end, we run Beanwalk on this firmware. And yeah, we got a lot of file systems. That's right. That's cool. But the fact is that when we extract the UBI partition, so which is all the file system on it, then we faced an issue. This UBI file system didn't work. We weren't able to get the files or the file systems contained in this UBI volume. So this was a problem. So here it is. I used some specific tools, UBI reader, to extract all the data. And then it simply failed. We were not able to get this data. And it was very puzzling, you know, because normally this is a straightforward process. So we had a look at the X file, because we got some kind of stack. And in the X file, we had a specific look at 0 pages. 0 pages are in flash memories, mainly some pages full of zeros. And this is very interesting because if you expect some oddities in the file, then these 0 pages or FF's pages, this is quite the same, might have some errors in it. And in this dump, we found that at a very specific position in almost each pages, we found a weird byte, and we didn't know what this byte is for. We didn't know if everything was normal. Then we had a look at the UBI partition we found, and this partition doesn't start at a very the expected offset. We got a 1 byte offset from the UBI signature. So this is also something uncommon with this dump. So this is some kind of crappy byte we got. And also we can see on the bin walk output that the address, the offset of the UBI data is 21C0001, which is not common. Most of the times we got a multiple of the page size offset. So this is not aligned on the page size at this time. So that's weird. We did a quick investigation, and this quick investigation revealed anomalies on the system. Our dump seems okay. This is correct. We got the correct size, and we didn't do anything wrong, you know, when we extracted the dump. So this may be related to the IMX platform. Maybe why not a custom storage mechanism? So let's have a look at this platform. This IMX platform is dedicated to industrial applications. So this is the integrated multimedia application processor and the family of processors. You can find IMX 28, IMX 5, 7, 6, 8. And this is very popular in automotive and home automation industries. So you can expect this platform on a lot of devices, such as the ones that are in ECUs, in cars, for instance, or maybe in the home automation devices. And this platform provides a lot of features, including an encrypted RAM, SATA 2 support, secure boot, and so on. So this is very convenient for people who want to create an industrial system to use this platform. So it's based on the ARM Cortex A9 control CPU for this IMX 28. So this image is extracted from the reference manual available on the internet. So I didn't do anything that other than just browse the internet and find the reference manual to get the information. This system can boot on various storage devices, such as NAND flash, SD cards, parallel NOR flash, USB, MMC, and also hard drives. So this boot process is handled by a specific boot ROM inside the IMX system, and this boot ROM starts the whole system. If you tell the system to boot on a NAND flash, then it's going to load the NAND flash and boot the system. So that's it. This is not very complicated at this time. But we spotted something very unusual, the general purpose multimedia interface, also called JPMI. So this JPMI component controls how data is read and stored on non-flash chips. And this is what this is at this time that becomes everything becomes interesting, because it supports also multiple non-flash chips. You can put multiple chips, map them on multiple partitions, and load it on the systems. This GPMI component also uses BCH, which is a error control and correction mechanism to avoid errors on reading and writing. In the same reference manual, there is a little image of what the flash memory looks like. On the top, this is the common layout used in non-flash memories. So this is very, very common. You got the 2 kilobyte main array, which is what is expected to be the data, and then at the end, the OOB data. So this is the extra space put by manufacturers along with every pages. So on the bottom, you get the layout used by this GPMI component, and it is totally different. So how does it work? Your data is split in 512 byte chunks. Then ECC bits are appended to this data. So this ECC data is stored as bits. This is not aligned with bytes. So this has a very specific consequence that it will shift all your data with maybe 2, 3, 4, 5 bits. And you have to reconstruct the old stuff if you want to deconstruct this specific layout. So ECC bits are added, then chunks are grouped and stored in a page, preceded by one metadata block. The size of this metadata block can vary. It depends. And a byte block marker byte is swapped with the first metadata byte. Sorry, if you have a look at this image, there is a swap byte. The first byte is in fact one byte taken from the last block and put in at the offset 0, and is replaced with one byte from the metadata. And this is very interesting because it can explain some anomalies we found. Remember the weird byte we found in the data page? This can be explained by this byte swapping stuff for byte block markers. So this is a byte that is normally from the metadata byte, but this byte has been swapped because of the storage mechanism used here. All of this information, all of this structure, and all the sizes are defined in a firmware configuration block, also called FCB. This structure contains all the required information about how data is stored. This structure must be present in the first megabyte of your non-flash. And the second field of this structure contains the ASCII text FCB. So if we look at our dump, we find this FCB signature at the very start of at the very beginning of the flash dump we made. So this makes sense. We got this structure. So let's have a look at this structure. If we look in the documentation, in the datasheets, and also in some codes we find on GitHub, this structure contains the non-space data size and also the OOB data size. So this is quite interesting. But furthermore, there is also some block 0 and block n specifications, such as the block 0 size and the block n size. They made some distinction between block 0 and the remaining blocks stored in the page. But in fact, it's quite always the same. And also, we can find the number of bytes stored in the metadata block. So if you want to determine how many bytes are used to store the metadata information at the start of the page, then you can get this information from the FCB. So this is a critical structure we need to find and parse in order to know exactly how data is stored in this non-flash. If we have a look at this structure in our dump, the offset 3C, we find the number of bytes of metadata block, and this number of bytes is one byte of metadata blah, 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 blah. I'm going to, do it. 1 byte of metadata block. So if we, again, have a look at this flash dump we made, then this can explain the offset we saw in the UBI image. Because this byte here, which is full of 0, which is 0, is obviously this metadata byte. But remember, this byte has been swapped with some bytes in our 0 page. So this is full of 0 then. And so this means that the 0 value we got here is the 0 value, 0 byte, we may expect to find in the last block. And if you have a look at the weird byte that is stored further in memory, then you will find that this byte is FF. And in the documentation, it's expected to be FF in the metadata. So it makes sense. There is also DBT, which is the discovered bad block table. So the GPMI components implement some kind of bad block management system. It implements its own way of managing these bad blocks. And this is done, again, with some specific structures. And these structures specify the number of bad blocks and the number of impacted pages by these bad blocks. So basically, what the GPMI does here is just read this DBT information. This is a list of bad blocks, and then remove the bad blocks or don't take care of these bad blocks when dealing with the non-flash. Going to read or write. When it comes to the ECC, again, this is an image extracted from the reference manual of IMX28. You have a nice overview of the storage in one page. So the first part is here, M is for metadata, and then we got all the blocks. Block 0 with its specific size, ECCB 0, so this is the ECC data for ECC bits for the corresponding block, block 0, and then with block 1, block 2, block 3, and so on. So this ECC is very interesting because, as I said earlier, the non-flash systems or non-flash chips are prone to error. So when we are going to read and extract information from these chips, we may have some bits flipped, and this can cause issues when you will try to extract file system from this firmware. So if it would be cool to be able to fix these errors and use these ECC bits to extract correctly data from this chip. So this ECC is based on BCH, which stands for Bose, Ray, Chowdhury, and Okegen error correcting code. So this is widely documented. It's also implemented in Python. So if you want to use it with a Python script, then you can use the corresponding library. So this is very, very common, very standard. But the fact is that the data from each block may be shifted from a certain number of bits. So this is the main issue here. You have to reconstruct every block by taking care of this bit shifting. And it takes a lot of time to do so. In the tool I wrote, this is the part of the code that is the less performant, because it takes some time to shift everything and reconstruct this system. So this bit shifting is taken into account by the GPMI component itself from a hardware perspective. So this is very, very quick and very efficient in the IMX architecture. But in fact, it may come some issues if we want to extract this data from the system. So what's next? Yeah. So what's next? We're going to take our flash dump and then try to recover all the data from this dump, knowing all of this. We know actually at this time we know how this data is stored in this device or in this non-flash. We know how to handle all the data stored in our flash dump. So let's go. We are going to recover and remap all the bytes. So first, we need to find the FCB structure at the beginning of the flash dump. So this is quite easy. Once you get the FCB structure, you can parse it and recover every critical parameters, such as the block size, ECCB block size, number of bits of ECCB. You can also get the number of bytes of the metadata and so on. So once you get all this information from the FCB, then you know exactly how the data is stored in this non-flash chip. Then we remove every metadata and ECC bit according to this FCB. So we are going to remove all the ECC bit information. We are going to remove the metadata as well. The idea behind this is to reconstruct a basic page from the IMX version of it. And of course, we are going to use this ECC bits to fix errors in the dump we made. So if our programmer may get some weird data or some bits flipped in the page, we can fix them and then have a more reliable dump that we are going to work with. So at the top here, you got the IMX memory layout. And what we are going to do is this. We are going to recover every piece of data stored in various blocks. And we are also taking care of the swap byte, which is written at the very beginning of the page, and put this byte back in the correct block. And we are going to do this for every pages in our dump. So if you want to do this manually, this may take a lot of time. So this is why we're going to create a tool. So we developed a specific set of tools called the IMX NaN tools. So this tool has been published on PyPy and also on GitHub. So if you want to have a look at this tool, the source code and so on, feel free to do it. Actually, it's written in Python and only in Python. We are thinking about a native version, maybe a C version of this tool, because like I said, it takes a lot of time to process all this bit shifting. So expect in order to give you an idea of the time you need to process a dump, this 1 gigabyte dump, it takes about 10 minutes to process and to recover the memory, the original memory layout. So this is not very efficient, but it does the job. So here we are going to extract information from this FCB. So we are going to use IMX non-info. This tool extracts the contents of the FCB and displays every field. So you can see the number of bytes in each pages. You can see also the size of the out-of-band data. You can get also the sizes of the various blocks, the type of BCH of ECC used. There are multiple versions of it. You can set up different parameters for the BCH algorithm that will use more or less bits for the ECC. So it depends. We got everything we need to extract it. And at the bottom of this output, you may see that there is two firmwares, firmware number 1 and firmware number 2. These firmwares are dedicated to boot, to the booting process. If you set up the system to boot on a non-flash, you can set it up to boot on the first one, first firmware or second firmware. So this is some kind of executable code that the IMX processor is able to run. So this is not where you're expecting to find the data or every partition. So you can extract it with the following tool, but it gives you just binary data you need to analyze. So again, it takes 10 minutes to process a 1 gigabyte file. So I sped up the video a bit just to show you this process. But in fact, this is actually working. I also specified the -C option to enable ECC correction. So it uses the ECC bits to fix all the blocks. And we are able to get a very reliable page or flash dump here with this tool. So this is the IMX non-convert. So this is the second tool of this tool set that can be used to convert an image. So once we converted this image, we can again use binwalk to try to find out, to extract the file systems that are stored in it. So if you look carefully, you will see that now the UBI offset is aligned on the page size. So we can process it very easily. So I'm going to extract the UBI volume by using DD. So this is some command line voodoo, very, very easy to do. And then I'm going to use UBI reader to extract all the files, all the file systems, and then on the files. So here it is. Yeah, we got everything, no errors this time. Everything works fine. And I'm going to extract all the images. Again, no errors, so that's pretty cool. And here they are. We managed to extract all the images from the UBI container without any problem. So this is great. And then we are going to extract all the files. So if you are familiar with UBI system, just to give you an overview of what is this system, it stores data in volume. So you have to do it in two steps. You first extract the images of each partitions, and then you extract files from each partition. These partitions may use some well-known file systems such as SquashFS or or other file systems. But UBI also comes with its own file system called the UBI FS. And most of the time, it's this file system that is used to store data. So again, we are going to use UBI Reader to extract all of this information. So as I mentioned earlier, this tool is it's pretty cool. It's written in Python again, so the source code is available on GitHub. You can use it to do a lot of stuff with this UBI system. And then by using this tool, we can extract from each image all the files from each image or file systems. We can get back the data and continue to analyze this device. So this is something quite unusual here, but we managed to handle this. So that's quite a win. So some remarks about this IMX system. So this IMX system, every reference manual can be found on the internet, either published by NXP itself or Freescale, or by a lot of developers that own some personal websites and publish on their website these reference manuals. These manuals are 1,000 pages long, and you need to go through these manuals to get all the valuable information. But in fact, this is open source. This is open source information you can gather from the internet. So there is no hidden information from NXP or Freescale. Also, a lot of publicly available, a lot of code is available on GitHub, and if you crawl many GitHub repositories, you can find a lot of mentions of the FCB structure and also the MTD driver. If you go on GitHub in the Linux kernel source code, you can find some drivers handling this GPMI component GPMI system. So in this source code, you can find everything you need, such as the details of this FCB structure and also the way the ECC works. So this is quite, this is not very obscure, you know. You need to gather every piece of information and put it together to understand how it works. But in fact, anybody can do it. So this is an extract of the IMX Knobs GitHub repository, which is managed by NXP. So this is a legitimate repository. And in this repository, we can find the FCB block definition. So this is quite straightforward to get this information. The fact is that you need to search, to look for it to get this info. Again, some code extract from GitHub. From this time, the U-boot source code. And U-boot contains some specific code for IMX system, IMX28 especially. So this is IMX28 non-gate ECC strength. And this is the formula to compute the size of your ECC bits, ECC block, depending on the page data size and PGOB size, so the specification of your non-flash. So this is quite interesting because you can expect non-flash to have this number of bits of ECC depending on these settings you can get from the datasheet itself. So the main concern here is that this IMX systems allows data encryption. You can use on-the-fly encryption for your non-flash or even your SD card or eMMCs, which are different ways to store data on an IMX system. But this system supports this non-flash encryption feature. So this is possible to use this encryption. But guess what? Most of the systems we analyzed, we tested, and this didn't use this feature because, you know, it's more convenient for vendors or manufacturers not to use this encryption process. So this is something, common in the embedded device industry. I can say it's difficult to set up for some people. It's difficult to set up this encryption mechanism, so they don't use it. And there are also some non-variants of this GPMI component, because we found some repositories on GitHub with different versions of this GPMI component, and most of the time these various or different version of this GPMI driver depends on the boot ROM put in the IMX system. Remember, I told you at the beginning of the talk that there is a specific boot ROM embedded in the IMX processor. So this is something that has evolved over time, and they also made changes to this FCB structure and other structures as well. So you may expect some issues. So the current version of IMX non-tools work for all of our dumps, but maybe it was for the latest version of this boot ROM. We didn't have the opportunity to test it on various versions of this boot ROM, and especially older versions. So the only way to know is to install, test, and contribute to this tool. So we are open to pull requests on GitHub, and if you want to test it, if you find some bugs in this tool, feel free to collaborate and to file a pull request. So as a conclusion, IMX systems use a custom non-flash layout, undocumented till now. This layout is documented in various documents and publicly available code. There is no very specific explanation, a very detailed explanation of how this layout works, but all of this information is split around various documents. So this explains why it's not documented. IMX non-tools, this is a tool we developed, provides a set of tools to handle this layout and convert dumps into usable images. So that is a way to solve this issue. And of course, IMX systems should use non-flash encryption feature to avoid key, passwords, or IP leaks from them. So just to conclude, I got a call from the product security incident response team manager a few days ago, and this guy explained to me that they are expecting some storm for their customers, coming from their customers. You know, a lot of customers of NXP use this IMX system, and at least for the recent years, they were expecting some kind of security because nobody was able to extract the data from the non-flash chips because of this custom layout they are using. But in fact, they are going to, I hope, discover that this custom layout is no longer undocumented, and maybe it will make this customer move forward in terms of security and maybe use this encryption mechanism. So who knows? But in fact, this is very common not to use encryption in the various devices we tested. So thank you for attending. If you have any question, no, nobody? Yeah?
I try to monitor the CPU read the flash through the pins, and I see that use 1 page only read 1 kilobytes plus 30 bytes control bytes. And about the manual said that 1 page should be 4 kilobytes. So is there an explanation for this kind of operation?
So if I don't understand well, you monitor the CPU and you saw that it reads 1 kilobyte plus 13 bytes on a page, where the datasheet stated that it's a 4 kilobyte page.
4 kilobytes plus 200.
Yeah, 224, for instance. Yeah. I got no explanation. Maybe it's some kind of variant of a specific version of a chip. You know, when you go through the datasheet, there are some specifications that are very standard, such as the one I showed you. But in fact, there are some some variants of non-flash chips in which the page size may change. So be sure to take the correct datasheet when you are doing this. It may be an error from the documentation itself. You know, sometimes people writing this documentation, these datasheets may do some errors, but in fact, it's not so common. So either you got the wrong datasheet, or maybe the software that uses this flash chip may consider that this flash chip has only a 1 kilobyte page, 1 kilobyte page size, and that's it. So basically, maybe this software thinks that this flash chip is only 1 kilobyte page size, and then it uses just a part of it to store the data. I don't know. This can be both. You know. Yeah. I didn't get it, sorry.
You mentioned that in the UI pages, there contains some metadata and some data.
Yeah.
So if the CPU tries to read out the data from NAND flash, should the CPU read out the metadata under the ECP path?
Yeah.
So CPU will do the ECP collection.
Sorry, I don't understand. I wish maybe we will talk about it later, so to have more clear idea about what you're talking about. Yeah. Okay. Anybody? No. Okay. Thank you for attending. It's